Hello and welcome back, Kamal here, and today we're going to be talking about a couple of really cool infinite series results involving the Riemann zeta function, the number pi, and even integers. Okay, cool, and in fact I have evaluated one of these series for the general case a while back, but I'm going to make use of a different approach relative to that solution development. So we'll start off with the sum s sub 1. Now this thing is the sum over k from 1 to infinity of -1 to the k minus 1 of zeta 2k divided by pi to the 2k. Now what we'll do here is expand the zeta function as an infinite series. So we have the sum over k from 1 to infinity, -1 to the k minus 1 divided by pi to the 2k times the sum over n from 1 to infinity of 1 by n to the argument of the zeta function, in this case being 2k. Okay, cool. Now take notice of the fact that this thing here is independent of the index variable n, so we can take it inside that operator. So we have the sum over k, sum over n, of what exactly? We have -1 to the k minus 1 divided by pi to the 2k times n to the 2k. And we can switch up the order of the operators here to now get the sum first over n from 1 to infinity, sum over k from 1 to infinity of -1 to the k minus 1 divided by, we'll write this as pi squared n squared to the k. And now notice that we have a really nice geometric series here, where the first term, a naught you may call it, is in fact 1 by pi squared n squared, and the common ratio is -1 by pi squared n squared. So that means we have the sum over n from 1 to infinity of 1 by pi squared n squared divided by 1 minus -1 by pi squared n squared, so that's a plus sign now. And all we need to do now is expand using pi squared n squared. So we have the sum over n from 1 to infinity of 1 by pi squared n squared plus 1. Now to make use of a really cool infinite series result, that is the sum over n from 1 to infinity of 1 by n squared plus a squared. And I have made a video solving this infinite series using complex analysis way back in the day, back when dinosaurs roamed the earth and all that kind of stuff. Link in the description below. So this thing equals -1 by 2a squared plus pi divided by 2 times a times the hyperbolic cotangent of pi times a. Okay, cool. So we'll modify the look of our infinite series just a little bit. We can factor out the pi squared term, so that gives us 1 by pi squared outside times the sum over n of 1 by n squared plus 1 by pi squared, meaning that the value of a in this case is going to be 1 over pi. So this implies that s here equals 1 by pi squared times -1 by 2 times 1 by pi squared plus pi divided by 2 times 1 by pi. And of course we have the hyperbolic cotangent of pi divided by pi, so there's some cancellation there, and we have hyperbolic cotangent 1. Okay, cool. So simplifying this a little bit, expanding the multiplication by 1 by pi squared, we see that we have -1/2, and then we have expanding this thing by pi will yield a pi squared up top. That'll cancel out with a pi squared down there, so we're left with 1/2 of the hyperbolic cotangent of 1. So we can write this as hyperbolic cotangent 1 minus 1 divided by 2, but there's a much better way to express the final result. Hyperbolic cotangent means we have hyperbolic cosine of 1 divided by hyperbolic sine of 1. And hyperbolic cosine is e to the x, in this case 1, minus, plus e to the negative x, which is e to the -1 in this case. So we have 1 by e, and this thing is divided by 2, but of course we'll have some cancellation because of the sinh function downstairs. So we have e minus 1 by e divided by 2 minus 1 divided by 2 again, the cancellation I was talking about. And on simplifying the e's and 1 over e's, we have e squared plus 1 divided by e divided by e squared minus 1 divided by e minus 1 divided by 2. So that's quite a tower of e's we have here. So there is some cancellation, further cancellation that is. So we have e squared plus 1 divided by e squared minus 1 divided by 2. And again, some simplification is in order. We have e squared plus 1 minus e squared plus 1 divided by 2 times e squared minus 1. So these two cancel out. The 1 plus 1 gives us 2 in the numerator, which also cancels out with the 2 downstairs. And we have this really awesome looking result. That is the sum over k from 1 to infinity. That summation operator looked absolutely horrible. This one looks much better. Of negative 1 to the k minus 1 of zeta 2k divided by pi to the 2k. So notice that we have zeta, pi, and we also have 1 by e squared minus 1 on the right hand side, which is absolutely gorgeous. Now, what about the other infinite series? Well, the other series was assigned as a homework problem to my supporters on Patreon, or maybe it was the series in orange. Anyway, one of them was assigned as a homework problem. And here's the solution. So we have the zeta terms, we have the pi terms, and the only thing different is the case that we don't have the alternating plus and minus signs. So this thing here is defined as the sum, and this is not the yellow color I normally use. Where did it go in my color palette? Gotta be somewhere. That one's far too bright for my taste. You know what? I might as well go back to purple. So the sum s sub 2 is defined as the sum, again, that looked horrible. Rather, that actually looked pretty damn cool. Yeah, that is one weird looking summation operator. So we have the sum over k from 1 to infinity of zeta 2k divided by pi to the 2k. And again, we'll expand the zeta function as an infinite series. So we have the sum over k of 1 by pi to the 2k times the sum over n from 1 to infinity of 1 by n to the 2k. And again, shifting this term inside the sum with respect to n operator and switching up the operators gives us the sum over n from 1 to infinity, sum over k from 1 to infinity of 1 by pi squared n squared to the k. And again, we have a geometric series. In this case, with the first term being, well, 1 over pi squared n squared again, with the common ratio being exactly the same thing. So s sub 2 equals the sum over n from 1 to infinity of 1 by pi squared n squared divided by 1 minus 1 by pi squared n squared. And again, we expand by pi squared n squared. We have the sum over n from 1 to infinity of 1 by n squared pi squared, terribly sorry about that, minus 1. Again, we can factor out the pi squared term from the denominator and get it outside as 1 by pi squared. And now we have the sum over n of 1 by n squared minus 1 by pi squared. And to evaluate this thing, we can make use of exactly the same infinite series, but this time we replace a by I times a, where I is of course the imaginary unit. So we have the sum over n of 1 by n squared minus a squared now equal to negative 1 over 2 negative a squared. So we have some cancellation there of the negative ones, that is. And we have pi by 2ia. What about the hyperbolic cotangent function? Well, we know that cotangent I times z equals, well, this should be I times, no wait, it's negative I times the hyperbolic cotangent of z. So we just replace z by I times z so that we have cotangent I squared z on the left, and on the right we have I times hyperbolic cotangent of iz. Now, I squared is negative 1, and we know that the cotangent function is an odd function, so we have negative cotangent z equal to negative I times hyperbolic cotangent iz. Okay, cool. And that's pretty much what we have here. we have the hyperbolic cotangent of, let me just write this out, terribly sorry about that, hyperbolic cotangent pi times I times a. And this thing would be equal to, well, the cotangent of pi times a with a factor of negative I, because, well, 1 over I is equal to negative I. So we'll just replace this by negative I times the cotangent of pi times a. We have some cancellation yet again, which is, of course, quite welcome because we can't have imaginary numbers as part of this result. So this implies that the sum, rather s sub 2, equals 1 by pi squared times 1 by 2a squared, a in this case being again 1 by pi squared, well, a squared anyway, plus pi divided by, no wait, negative sign, pi divided by 2 times 1 over pi, times the cotangent of pi divided by pi. Again, we have some cancellation and we're left with cotangent 1. So now we have, again, on expansion, 1/2 minus 1/2 of cotangent 1. And that's pretty much our final result for s sub 2. That is, we have the sum over k from 1 to infinity of zeta, terribly sorry about that, that's a horrible looking zeta, not much better, slightly better, and much better, zeta 2k divided by pi to the 2k equal to 1 minus cotangent 1 divided by 2. Interesting result indeed. And maybe we can just expand this in terms of sine functions and cosine functions so that we have sine 1 minus cosine 1 divided by 2 times sine 1, which is pretty interesting indeed. I'll give it that much. It does look pretty fancy. And I hope you enjoyed the video. More importantly, I hope you learned something from the video. Be sure to like and subscribe. Share the video to help, support the channel. Drop me a follow on Instagram, and in case you like the effort, you can support me on Patreon. Thank you. See you next time.